Today, we're diving into a major breakthrough that could totally rewrite the rules for solar power. And it all starts with a simple, kind of poetic idea: actually bottling sunshine.
I mean, just think about that for a second. What if you could capture the sun's energy in a liquid? Just store it and then release it as heat whenever and wherever you needed it. It sounds like something straight out of science fiction, right? Well, a team of researchers just took a giant leap toward making it a reality. So, why is this such a big deal? Well, the biggest headache with solar energy has always been that the sun isn't always out. It doesn't shine at night, it gets hidden by clouds, and that means we need these huge, expensive, and let's be honest, often inefficient battery systems to store the power we generate. This whole storage problem, it's one of the biggest roadblocks to a truly renewable energy future. And this is exactly where this new tech changes the game. See, with the solar you're used to, you need panels to capture the light, and then a totally separate system, like a big lithium-ion battery, to store that energy. But with this new approach, the liquid is the whole system. It absorbs the sunlight and stores the energy right inside its own molecular structure. The battery is the solar collector. It's all in one.
So where did the idea for a material like this even come from? Well, the answer is pretty incredible, and probably not what you're thinking. It wasn't dreamed up in some high-tech materials lab. Nope, it was found inside the very building blocks of life itself, our DNA.
You heard that right. When our DNA gets hit with UV light, it can sometimes form these weird little structures called Dewar lesions. Now, this is technically a type of damage to the DNA, but researchers noticed something amazing. These damaged parts hold a massive amount of strain in their chemical bonds, which is basically a form of stored potential energy. As the lead researcher Han Nguyen said, this natural strain was their big aha moment. In chemistry, think of strain like a compressed spring. It's just sitting there, packed with energy, waiting for a trigger to let it all go in a burst. The team realized, hey, what if we could engineer a molecule that does the exact same thing on purpose? Okay, so let's dig into how this molecular spring actually works. The science behind it is just so elegant, and honestly, that spring analogy is the perfect way to picture what's happening. This technology belongs to a category called molecular solar thermal, or MOST for short. The whole idea is pretty straightforward. Use molecules to grab energy from the sun, hold onto it, and then let it go as heat whenever you decide, on demand. This chart breaks down the cycle perfectly. First, sunlight hits the molecule. That jolt of energy forces it to twist into this tense, high-energy shape. That's like setting the spring. And here's the magic part. It stays locked in that shape, holding that energy pretty much indefinitely. Then, when you're ready, you apply a little trigger, like a bit of heat or a catalyst, and bam, the molecule snaps back to its original shape, releasing all that stored energy in a powerful burst of heat. And the whole process can be repeated over and over again. It's a truly rechargeable liquid battery. You charge it with nothing but sunlight, and you discharge it for pure heat. Okay, so the concept is really cool, I get it, but does it actually work? Well, this is where it gets really exciting. The results aren't just a small improvement. This is a record-shattering, game-changing leap forward. Let's just start with the headline number, 1.6 megajoules per kilogram. That's its gravimetric energy density, which is just a fancy way of saying how much energy you can cram into a certain weight of this liquid. And yeah, that's a new world record. Now, 1.6 megajoules doesn't mean a whole lot on its own, so let's put it in perspective. Your standard lithium-ion battery, the kind in your phone or an EV, holds about 0.9 megajoules per kilogram. Previous attempts at this kind of MOST tech topped out around 1.0. This new molecule, the one inspired by DNA, it hits 1.6. We're talking nearly double the energy density of a lithium-ion battery.
And like the researchers say, this isn't just about getting a high score. This incredible energy density finally solves the biggest problem that's held this technology back for years. It just wasn't powerful enough to be useful in the real world. Well, now it is.
If you're still not getting a feel for just how powerful this is, get this. The heat it releases is so fast and so intense that it can boil a small sample of water in less than a second. That's some serious power, and it proves this thing can work out in the real world, not just in a perfectly insulated lab. So, that's the bottom line. This stuff is finally powerful enough to be practical. So let's talk about what this could actually mean for us. How do we take this from the lab bench and bring it into our homes and our lives? Well, the really smart thing is that this material was designed for practical use right from the start. It's water-soluble, so you can just imagine it being pumped through collectors on your roof, charging up all day. It's tough, it works in normal environments, and best of all, you don't need a separate, clunky battery system. It's all built in.
And the potential uses are just, wow. You could use this for home heating, right? Store up all that summer sun to keep your house warm through the winter. It could be a literal lifesaver in disaster zones, providing on-demand heat for cooking or sterilizing water when the power's out. It's a way to get heat to places that are completely off the grid.
And believe it or not, the team isn't even done yet. The next big step is to make this molecule even more efficient. They want to design new versions that can soak up even more of the sun's light, and they're planning to use AI to help them sort through thousands of possible designs.
As researcher Kendall Hoke explains, they're going to be using some seriously powerful quantum calculations to design the next generation of these molecules, pushing for even higher energy storage. This field isn't just moving forward, it's hitting the accelerator.
Which kind of brings us right back to where we started, doesn't it? This whole world record-breaking technology began just by looking at a tiny twisted bit of DNA. It really makes you wonder, what other incredible solutions to our biggest problems are already out there, hidden in the natural world, just waiting for us to find them?